Everyone. What do you think about the title that you can see there? It says put it to practice. So what do you think about it? So let me make it clear to you. The reason why I'm doing this video is pretty simple. I, for one, firmly believe that whatever theoretical concepts that you are studying, or even sometimes by hearting for a subject, would do you no good at all whatsoever. So then what you can do, when you feel that particular confidence, you get confident on a subject only when you can put the concepts that you have learned into practice to solve different problems. That is the reason I gathered a small collection of problems from the internet until the concepts that we discussed till now, or overview of all the concepts, so that you can try to solve them on your own and see how good you are. This is just something that I wanted to do. Usually I do that in my class as well. From time to time, I put some small tests or quiz so that the student should be involved. Similarly, I'm doing this. So why wait? Let's get going. And also, if you know the answer, or if you feel that there is anything that you thought it would bring more, it would do more good, so please put it in the comment section and I will try to add that as well. So let's start with the questions. Most of these questions are collected from the previous GATE question papers and some from internet sources. Okay, so let me start with the first question. So you can see here, the first question, what it says is, it says a process executes the code fork, fork, fork 3 times. The total number of child processes created is dash. This is also given in one of those GATE things. You can see here. Now, one common rule that you need to understand regarding the fork system call is, for n number of fork system calls, we get 2 power n processes created. 2 power n processes are created. Out of this 2 power n, one process will be your original parent process. One process is the parent process. So in this particular problem, I have 3 fork system calls. So the total number of processes that are created are 2 cube. That means 8 processes. But in the question, it is asked that the total number of child processes created are. So the answer would be 2 cube, that is equal to 8 minus 1, that is equal to 7. If it is asked the total number of processes that are created are, then you can write as 8. But it has been asked as child process. So you need to answer as 7. So please do keep that in mind. It's a thumb rule. So how many forks you can see here? Based on that, please apply 2 power n, and then you can get that many number of processes. If you are clearly asked about child process, just subtract 1 from it. Now, let's go to the second question. The time taken to switch between user and kernel modes of execution be T1, while the time taken to switch between 2 processes be T2. Then it is asking me which one of the following is true. It has given me some conditions between these two particular timelines. So first, let me say that T1 is switch between the user mode, and that means you have to switch from user mode to kernel mode. That is a time taken, kernel mode, whereas T2 is the time taken for context switching. Context switching. So what is the relationship between these two? What can you say about these two? Now, generally, if you follow my earlier videos, I told you that we have something called as a mode bit. One bit which is mode bit, where the operating system will change this bit so that it can change the execution from user mode to kernel mode. So you usually, to change one bit, the time taken will be very less. Similarly, when you talk about T2, context switching, you have to understand that in order to do context switching, first this has to happen. So T1 plus whatever time it takes for context switching. So usually context switching time involves saving the state of the current process and loading the state of a new process. So it takes some considerable time. So as a thumb rule, you can say that when you compare these two things, because there is always something here, whatever X you can say. So generally T1 will always be less than T2. This is the explanation for this. Okay, so the time taken to change the mode from user mode to kernel mode will always be less than the time taken to do context switching of a process, because context switching process usually takes time to save the context and also the restore of the context of the new process. Now, let us move on. The third question which I've got is, let me read out. A thread is usually defined as a lightweight process because an operating system maintains smaller data structures for a thread than for a process. In relation to this, which of the following is true? There are given 4 options. So in these 4 options, you can also find that on a per thread basis, the OS maintains only CPU register state. The OS does not maintain a separate stack for each thread. On per thread basis, the OS does not maintain virtual memory state. On per thread basis, the OS maintains only scheduling and accounting information. Now, if you're good enough, you can, if you remember the threads lesson which we discussed earlier, anywhere I did not discuss about virtual memory. Usually, virtual memory is always associated with a process. We never associate virtual memory with a thread basis, right? So this is actually true. In order to understand, because it says that the OS does not maintain virtual memory state. That's what I've been saying. It only maintains a virtual memory for a process. It never maintains it for a thread. But what about the remaining 3 options? For these 3 options, I don't know if you remember this or not. I have shown you a diagram how a multi-threaded process looks like. What are the things that it shares? Now, if you remember, usually we have a common code section, we have common data section, and we also have a common file section. These are shared among threads. And if you remember, let us assume that there are 3 threads that are running for this particular one process. This is all one process. Okay. Now you have separate registers for all registers, each and every thread. And similarly, we have separate stack for these things. So imagine this is one thread, this is one thread, this is one thread. You have the same thing, registers each thread, and we have stack, So on a per thread basis, the OS maintains only CPU register state. No, it maintains all these things. It maintains stack, it maintains code, it maintains data, it maintains files. So this is not true. The OS does not maintain a separate stack for each thread. So you can see here for each thread, it maintains a stack state. So this is also false. And on a per thread basis, the OS maintains only scheduling and accounting information. It's not. It has to maintain the register information, the proc counter, and also the stack information. So the remaining 3 options are false. The only option that is true here is that OS does not maintain the virtual memory state. You can do this by simply reading these things, or you can actually go through this way also. Okay, so this is how you maintain for a thread. We call this as a multi-threaded process, where there are multiple threads that are running that belong to the same process, because the threads share the same address space of the process usually. Let me check this out. The next question is, consider the following statements. The operating system asks for Bob's password when logging in. Bob is denied access to write to a certain file, whereas he can read it. Now pick the correct statement. It has given me 2 statements, 1 and 2. Now it is asking me what is 1 and what is 2. One is authentication. So rather than going through this, if you are good at security, just remember that this statement is going to tell you, it is going to identify whom you are, whether you are the person you are or not. So it's asking. So this is nothing but authentication. Authentication is proving yourself. Okay, proving your identity. So this is authentication. Then after that, if you read the second statement, it is saying Bob is denied access to write to a certain file, whereas he can read it. This comes under authorization. What do you mean by authorization? Authorization is something which the OS checks if you are permitted or if you are allowed to do so or not. If you open a file, if you are a guest, if you do not have a privilege to execute a particular file, it will not allow you to do that. It will say that please go get the administrator password or log in as an administrator. You must have come across this, right? So the first statement is authentication, whereas the second statement is authorization. That means if you are verifying whether the user is permitted to do that particular action or not. So this is what one is authentication. Authentication means verifying your identity. You are actually verifying whether it is Bob or not. If Bob's password does not match, you will not grant him access. So this is your answer. See, one is authentication, whereas two is authorization. Let me check the next question. Now, which one of the following is false about the operating system? There are 4 statements. Let me read them out. OS code assembly consists of a bit of assembly code. Yes, that's true. Okay, we are asked to find out which is false. OS communicates with hardware devices directly. Yes, that's the definition of OS. OS is independent of the hardware on which it executes. I don't think so, because based on the hardware only, the OS is dependent on the hardware. Actually, it says independent. So this is false. Timing plays a crucial role in an operating system. Absolutely true. So the answer, which one of the following? So obviously, the answer for this is C. OS is independent of the hardware, because OS is purely dependent on the hardware for it to get the job done. Now, system calls are usually invoked by using dash. By what? Now, this we have studied in our system calls also. The direct answer will be a privileged instruction. You have to use a privileged instruction to invoke the system calls. This software interrupt, calling, interjump, these are not the answers. You can say that the system calls are usually invoked by using a privileged instruction. Said, let me move on. Now it is asking, there is a question here. It says, consider 3 CPU intensive processes which require 10, 20, 30 time units and arrive at times 0, 2, and 6 respectively. How many context switches are needed if the operating system implements a shortest remaining time first scheduling algorithm? Okay, maybe I forgot. We haven't still covered. This is called as SRTF algorithm. I will be posting the videos of the scheduling algorithms. You can check out those videos. But anyhow, it is asking me just about the context switches only. You can see here there are 3 processes, right? 3 processes. So let me draw you a Gantt chart. Usually a Gantt chart is used to represent the timing of the processes, scheduling. Now, the first process arrives at time 0. So it arrives. Let us assume that the 3 processes are P1, P2, and P3. Okay, so P1 has arrived and saying the shortest time first scheduling algorithm. Okay, now first process requires 10 seconds. It says 10 units, but for my explanation sake, I'm treating them as seconds. So P1, once he's been granted the CPU, it executes for 10 seconds. And then at time 2, P2 comes in. So P2, because this we need to explain SRTF a little bit, but simply I'm saying that next comes P2. Usually in SRTF, we find out whether to preempt this or not, but let me save that for my SRTF video. I don't want to get you too much confused. So P2 and finally P3, 3 process, right? So P2 continues for 20 seconds. So at 30, it executes and then you close it at 60. So it is asking, do not count the context switches at time 0. There are 1, 2 context switches, 3, and 4. It is asking, don't worry about these 2. Here the context has switched from P1 to P2. Here it is switched from P2 to P3. So how many? 1, 2. Because it says that you don't bother about at the initial, at time 0, and at the end, only tell me how many context switches are required. So 1 and 2. The answer is 2. Because only I can see that there are 2 times it has changed state, P1 to P2 and P2 to P3. We'll discuss about the scheduling algorithms and this Gantt chart in detail when in my FCFS video. Please do check that out. And then we'll also discuss about SRTF. Okay. So let me move on. This says that a computer handles several interrupt sources, of which the following are relevant for this question. Okay. Interrupt from CPU temperature sensor, interrupt from mouse, interrupt from keyboard, interrupt from hard disk. Okay. It says raise interrupt CPU temperature is too high. Mouse raise interrupt if the mouse is moved or a button is pressed. Okay. Interrupt from keyboard, raise interrupt when a key is pressed or released. Interrupt from hard disk, raise interrupt when a disk read is completed. So which one of these will be handled at the highest priority? Of these 4, which one do you give the highest priority? Once again, if you use your common sense a little bit, you can see that of all these 4, the highest priority or the event, if delayed, will have a large impact is this. Because if the temperature sensor is not bothered, if you are not bothering about the temperature sensor, if the temperature becomes too high, the CPU might get burnt. So obviously, the CPU usually handles interrupts or assigns priority to the interrupts based on their impact. Generally talking, for mouse and keyboard, because these two are low speed devices, the interrupts will be assigned less priority. High priority comes to the hard disk, and then priority comes to the highest priority should be given to the CPU temperature sensor. Simply because if you ignore this interrupt, the CPU there is a huge impact because the entire CPU might get burnt. The answer will be D. Here the answer is D. Highest priority is D. If they ask you what is the order, then after CPU temperature you can go for hard disk, and then comes the keyboard and mouse. Okay, so these is how it assigns the priority. As a general rule, the CPU assigns priorities on the impact that it might have, the impact of the interrupts. So let me move on. It says the next question is, with the dash, only one process can execute at a time. Meanwhile, all other processes are waiting for the processor. Continuation, with the dash, more than one process can be running simultaneously, each on a different processor. So obviously it says that each on a different processor. This automatically means that there are multiple CPUs present, and in case of multiple CPUs, we call it as multiprocessing systems. So my answer will be either this or this, multiprocessing. And here in the first it says only one process can execute at a time. Automatically it means uniprocessing or uniprogramming. All other processes are waiting for the processor. I can say that it is uniprogramming. In uniprogramming, the CPU will only execute one process, and only after completion of that process only the CPU can go to another process. It cannot switch between different processes at the same time. So your answer will be D. Uniprogramming and multiprocessing. You can simply say that each on a different processor. Automatically you should get the idea that there are multiple processors present. If you mean that multiple processors, we call it as multiprocessing systems. Now let me go on to the next one. Select the correct order of events after power is initialized on a system. There are three events here. The first one is bootstrap loader is loaded from the disk. Kernel is loaded onto the memory. Firmware ROM loads boot block. The first thing it does is you have to locate the boot block. So the order will be, the first one will be third statement, and after loading the boot block, the bootstrap loader is loaded from the disk. You can have to find the bootstrap program, then it is loaded. So it will be the next one. And finally, after this is loaded, then it will look at the kernel, and the kernel is loaded into the memory. Only then the control will be handed over to the operating system. So the order will be 3. First, the third statement will execute, first one, and then this is the second one, and this is the third one. This is the order. It is done. This is the correct order of events after power is initialized on a system. Now, which of the following does not interrupt a running process? A device, definitely it can interrupt. Timer, if it runs out, it has to send an interrupt. Even a power failure also will interrupt. A scheduler process is going to deal with scheduling. It only selects the jobs. It will never interrupt a system. So the answer will be a scheduler process. Okay, because the remaining 3 will obviously can create an interrupt, whereas the scheduler process only deals with selection of process for placing into the main memory, or even selecting the process from job queue into the ready queue. So it will never create an interrupt. Okay, so next one. How many times the following C program prints yes? Okay, this we actually discussed earlier. There are 2 forks here. So obviously 2 square, 4. So out of 4, 1 will be parent and 3 will be child process. Okay, so obviously the answer will be C, 4. It says how many prints yes. So the 4 times it will print yes, because there are 4 processes that are created. So these are a small collection of questions that I brought for you guys. If you like such videos, if you want me to continue doing these videos, please say so in the comment section. As I said, I'll be discussing different questions at different steps of my lectures. So next I want to do some on the scheduling algorithms, scheduling criteria, and so hope you enjoyed this, and thank you very much. Take care.